Hello, everyone. My name is Jake Hawkins, and I am the project manager for the University of Illinois at Urbana-Champaign RASC-AL team. I am joined by a few of my team members who will introduce themselves throughout the presentation. We chose to design an architecture for Theme 3 Short Surface Stay Mars mission due to its importance as one of the next major milestones in space exploration. The architecture we created is called the Space Habitat for Interplanetary Exploration and Life Discovery, or SHIELD for short. Let's start off with the objectives and requirements for Theme 3. The two mission objectives for this theme are to achieve the first human landing on another planet and search for life on Mars. Searching for life on Mars greatly impacted how we structured the surface operations. In addition to achieving these two objectives, SHIELD also satisfies multiple other requirements set for Theme 3. The full list of requirements are shown on the right. In a few cases, SHIELD even exceeds the base requirements. The crew leaves Earth in April 2033 instead of sometime in 2035 to take advantage of a lower delta-V requirement than most transfer windows. Additionally, SHIELD only needs 2 landers as opposed to the 3 landers allowed by the requirement. The mission starts with Transfer 1 using the Hohmann transfer window in 2031 to deliver Lander 2 to areosynchronous orbit. Then, in late 2032, Transfer 2 delivers Lander 1 into a hyperbolic Martian entry which occurs in July 2033. Lander 1 carries Rover 1 down to the surface, which then exits Lander 1 and starts exploring Mars before the crew arrives. Transfer 2 is discarded into interplanetary space. The crewed phase of the mission begins in April 2033. Transfer 3 takes the crew, SHIELD crew module, and Orion to areosynchronous orbit and rendezvous with Transfer 1. Lander 2 and the SHIELD crew module undock from their respective transfer vehicles, and Orion transfers 2 crew to Lander 2. The SHIELD crew module and Orion dock to Transfer 1, and Lander 2 docks to Transfer 3 and uses it to go to low Mars orbit. Lander 2 then carries the crew to the surface. Upon landing, the crew will begin the 30-day surface mission and use the rover to collect soil samples. Once the surface mission is complete, Lander 2 takes the crew and their samples back to Transfer 3, which then rendezvous with Transfer 1. Orion retrieves the crew from Lander 2 and returns them to the SHIELD crew module. Transfer 1 then delivers the crew back to Earth, and Orion is used to re-enter Earth's atmosphere. Transfer 1 and the SHIELD crew module are discarded into interplanetary space.
Hi, I'm Justin Herman, and I'll be going over the timeline and cost of the SHIELD mission. The research and development timeline is shown here. This occurs between 2020 and 2031. SHIELD research and design will begin in 2020 immediately following proposal acceptance, after which there will be about a 2-year gap before construction of the actual vehicles begins in 2022. This is to allow for facilities to accommodate having the resources to construct things for the SHIELD architecture as well as to finalize designs. Following this, the construction of the rover, transfer vehicles, and landers are anticipated to be completed by 2029, with Transfer 1 being completed in 2027, Transfer 2, along with Rover 1 and Lander 1 being completed by 2028, and Lander 2 finishing by 2029. Both SHIELD crew modules will be completed by 2031 in anticipation of their launch date in 2033. Significant mission operations will begin in 2023 and continue all the way to mission completion. At the very beginning, astronaut training and selection will begin. This is to allow plenty of time for the crew to be selected and then become familiar with mission equipment. Also, mock-ups for each vehicle will be installed in NASA's Johnson Space Center so the crew has time to familiarize themselves with them prior to launch. In 2027, the integrated propulsion system will be tested in space. It will start in low Earth orbit and then end up in high Earth orbit. This burn is done in space to protect ground staff and equipment in the unlikely event of a failure during testing. Following this, in 2031, Lander 2 and Transfer 1 will leave Earth and arrive in Martian orbit later in the year. In 2032, Rover 1 will leave Martian orbit aboard Transfer 2 and arrive the following year. Then, in 2033, the crew will depart from Mars via Transfer 3 and rendezvous with the rover and Lander 1 at Mars. They spend 40 days on the surface, and then eventually reaching orbit, they dock with Transfer 1 and return back to Earth. SHIELD currently uses 3 launch vehicles, one from Blue Origin, one from NASA, and one from SpaceX. Blue Origin's New Glenn rocket will be used to launch fuel tanks holding liquid hydrogen into orbit. NASA's SLS will be used to launch the Crew, Orion, and the SHIELD logistics module into orbit before their transfer to Mars. And SpaceX's Falcon Heavy is primarily used to launch the vehicle's propulsion systems as well as the SHIELD habitation module. For future consideration, SpaceX's Starship can be used, once it has been more validated, to potentially lower cost and also reduce the number of fuel tanks needed for the mission to be completed. The first SHIELD launch is in 2027 with the test of the nuclear propulsion system. In 2028, the propulsion system for Transfer 1 is launched into orbit. Then there are 18 separate launches of New Glenn, each carrying a liquid hydrogen tank for Transfer 1. These are scattered between 2028, 2029, and 2030. Then, in 2031, Lander 2 launches on a Falcon Heavy, and then 2 more New Glenns will launch liquid hydrogen tanks to rendezvous with Transfer 2. 2032 brings another propulsion system launch. This time it is Transfer 3, also aboard a Falcon Heavy. Following this, there will be 5 New Glenn launches throughout the year for the Transfer 3 hydrogen tanks. And then, Rover 1 and Lander 1 are going to be launched on a Falcon Heavy. 2033 is the year where the final launches take place, where aboard the SLS, the Crew, Orion, and the logistics module will launch, and then the habitation module for SHIELD will launch on a Falcon Heavy. Cost estimation for SHIELD was developed using NASA's Project Cost Estimating Capability software, or PSEC, coupled with manual calculation for the cost of the nuclear reactors. This manual calculation was done using an equation found in an update presentation for PSEC on NASA's NTRS. The cost of the design and development phase of the mission totals to around $28.48 billion in U.S. currency, while the construction, integration, and testing all will cost $12.28 billion. The launch costs all tally to about $5.06 billion, including all launch vehicles, and mission operations, which is scattered across the entire timeline, tallies to around $5.28 billion. This yields an entire mission cost for SHIELD of $50.74 billion in U.S. currency.
The propulsion system implemented in each transfer vehicle is based off nuclear thermal propulsion, where propellant is heated while running through the fuel elements of a reactor and then accelerated through a nozzle. Specifically, the system is made up of a cluster of 2 bimodal nuclear thermal rockets that use low-enriched uranium-235 and have cermet fuel elements made of uranium dioxide embedded in a tungsten metal matrix. It's bimodal because it can be used for propulsion maneuvers and power generation, which will be addressed in a later slide. Thrust level, core power, and specific impulse are listed in the table on the slide, and the propellant used is liquid hydrogen due to its low molecular mass. Now, this system is currently sitting at a technology readiness level of 3, mainly due to the fact that the fuel elements implemented in this design have not been tested at full scale yet. LEU CERMET fuel elements are being actively studied and tested at NASA, and we have set a mitigation strategy where if the fuel elements are not ready at a full scale by a certain date, the elements will be switched to LEU composite. Now, the LEU composite elements are further along in development, however, they are more prone to corrosion when liquid hydrogen is run through them. Nuclear thermal propulsion has higher thrust than electric propulsion and higher specific impulse than chemical propulsion, thus it offers increased payload capacity and a lower mission duration compared to those two systems. Lower mission duration means less exposure to cosmic radiation and microgravity, and nuclear thermal propulsion allows for unique mission abort options, including the ability to return instantly upon Mars arrival and wider injection windows.
The reaction control system implemented in both transfer vehicles and landers consists of various clusters of 4 AMBR thrusters that run on a hypergolic combination of nitrogen tetroxide and monomethyl hydrazine. The thrusters have the same physical envelope as the HIPAT thrusters, however they have a higher performance. Both thrusters are actually manufactured by Aerojet Rocketdyne. This RCS enables maneuvers at Earth's orbit, Mars's orbit, and during transfer, including rendezvous and docking, big course corrections, close attitude control, setting for retropropulsive maneuvers, and orbital maintenance. The nuclear reactors are also used to generate power for transfer vehicle operations. The reactors are kept idle rather than being completely shut down while not performing propulsive maneuvers during transfer, such that each reactor generates approximately 125 kilowatts of thermal power. A helium-xenon mixture is ran through the reactor core in a closed secondary gas loop, which can be seen in the schematics on the slide. The mixture is then rerouted to a Brayton rotating unit, which generates electricity at 20% efficiency. This means that overall, 50 kilowatts of power are generated while the reactors are in power mode.
While the nuclear reactors are providing thrust, solid oxide fuel cells would be used to produce power. They're also the main power system on the rover. Fuel cells were chosen for their reliability in deep space as well as on the Martian surface. Solid oxide fuel cells, which are being developed at NASA's Glenn Research Center, are unique from other types of fuel cells in that they use hydrocarbons as fuel. This allows us to use methane as well as ECLIST waste to generate power. They're also not susceptible to the coking or sulfur poisoning that plagues PEM fuel cells and have 5 times higher specific power density. Our cell stacks use ceramic interconnects to minimize mass as well as avoid oxidation and corrosion. Thermal control for the nuclear reactors will be handled by a conical pump-looped radiator. This radiator will reject waste heat from the reactors as well as low-level decay heat from the engines. In order to maintain a temperature of 23 degrees Celsius, resistors generating between 600 watts and 1.1 kilowatts will be placed in the crew cabin. The exterior structure of the SHIELD crew cabin is painted in electroless nickel and acts as an imperfect black body to account for electronics waste heat, ECLIST, and heat from the sun. For insulation, polymer cross-linked aerogel is used due to its low density as well as high functionality at ambient pressure, making it ideal for a deep space environment. The primary communication system on SHIELD is derived from the Deep Space Communication System being developed by Caltech's Jet Propulsion Laboratory. This laser communication suite, which is set to fly aboard NASA's Psyche mission in 2022, uses photon-efficient communications to deliver high uplink and downlink rates, including HD video capabilities. The communications relay placed into high Earth orbit during the Integrated Propulsion System Validation mission receives the signal from the vehicles and transmits it to the Deep Space Network via X-band radio. SHIELD vehicles are also equipped with an X-band radio system as redundancy. The transfer vehicles use an X-band omnidirectional antenna for convenience during rendezvous, and the rover has high-gain and low-gain antennas for easy communications with the SHIELD crew module. This radio system is sized to transmit all data except for HD video. SHIELD command and data handling consists of a combination of heritage flight controllers and systems previously developed for Mars missions. The system includes the RAD-5500 microprocessor, a computer chip hardened to endure the natural radiation and other conditions of deep space. This system is a successor to the RAD-750, which has flown successfully on the Mars Reconnaissance Orbiter and will fly again aboard the Mars 2020 Perseverance rover.
The Environmental Control and Life Support System, or ECLIS, is kept as common as possible between vehicles in the architecture, with the SHIELD crew module being the main element that the ECLIS is designed around, as over 96% of the mission is spent inside the vehicle. To improve mission flexibility and to help with redundancy, the main ECLIS systems are all located within the larger habitation module, while the logistics module contains most of the consumables and spare hardware needed for the mission. The primary subsystems and their masses are listed on this slide.
The net habitable volume across both modules is 85.5 cubic meters, which is 21.4 cubic meters per crew member. This is only slightly lower than the 21.5 cubic meters estimated to be optimal based on NASA Standard 3000. The internal layout is based on racks, like those used on the International Space Station, to increase flexibility and reconfigurability while also facilitating rapid development. To reduce the impact of microgravity, conventional, resistive and aerobic exercise devices, like those used on the ISS, were selected due to comfortable artificial gravity being impractically large for proper nuclear radiation shielding.
3 sources of radiation were considered for the radiation protection system: galactic cosmic rays, solar particle events, and the nuclear reactors. For galactic cosmic rays, a polyethylene stuffed Whipple shield at a skin density of 4.5 grams per square centimeter reduces the effective dose rate from GCRs by 10% to 56.8 centisieverts per mission at solar minimum. For solar particle events, a single tank filled with liquid hydrogen, which is needed for propulsive capture after each interplanetary coast phase, is placed between the crew module and the sun, reducing the effective dose to under 7 thousandths of a centisievert per solar particle event. Each nuclear reactor also has a beryllium, tungsten, lithium hydride radiation shield, which reduces the combined reactor dose rate to 23 centisieverts per mission, and with the help of the hydrogen fuel tank, this drops to well under 1 centisievert. This brings the total dose per crew member to under 58 centisieverts per mission.
The trade study for the atmospheric revitalization subsystem focused on oxygen generation, carbon dioxide removal, carbon dioxide reduction, temperature and humidity control, contaminant removal, and gas storage. When compared with alternative systems, each of these technologies outperform the alternatives by a large margin, beating out other technologies such as solid polymer waste electrolysis for oxygen generation and a 4-bed molecular sieve for carbon dioxide removal. While water is required to generate oxygen through electrolysis, some of that water can be produced by the Sabatier reactor, which is fed the hydrogen necessary for the reaction by the electrolysis reactor. This means only 0.569 kilograms of water are needed to produce 1 kilogram of oxygen, while the methane produced is used to run fuel cells on board the vehicle.
The trade study for the Water Recovery and Management System identified two primary competing systems. The first was vapor phase catalytic ammonia removal, while the second was a multi-step process of cascade distillation followed by filtration by reverse osmosis, with brine from both systems being processed by brine evaporation bags. While the vapor phase catalytic ammonia removal system did perform better in the initial trade study, better estimations of mass and spare hardware characteristics revealed that the cascade distillation system and reverse osmosis system had a lower mass, higher reliability, and improved water recovery rate from 98 to 99.5%, meaning only 203 kilograms of water need to be stored for the entire mission, including 10 days worth of excess water.
The waste management system leverages technologies under development at NASA, including the Universal Waste Management System being built for Orion for waste collection and the trash-to-gas reactor to process the waste. The benefit of the trash-to-gas reactor is that by gasifying the waste through pyrolysis, the products can be filtered for carbon dioxide, methane, or water if needed, or can otherwise be vented into space to reduce mass and increase open volume. The reason the trash-to-gas reactor was chosen over the heat melt compactor or other similar technologies was its ability to process fecal waste with the low risk of contaminating the rest of the vehicle.
This architecture utilizes a bulk storage system for food, which requires that food be prepared from ingredients, though a prepackaged approach is also developed in the event that the bulk storage system does not mature in time. Clothing, waste collection, hygiene, fire suppression, and medical supplies are based on heritage systems on the ISS. To size the spare hardware for this mission, a Poisson process based on the mean times between failures for each hardware component was assumed, which was then used to construct a product of gamma distributions at the subsystem and then full system levels. This distribution estimates a 99.71% probability that enough spares are carried to replace all failed components, which is a 1 in 350 chance of running out of spares, allowing additional risks to be factored in before hitting the 1 in 270 chance of failure required for the commercial crew program.
When designing the transfer vehicles, the team searched for an option that was extremely flexible. The final system the team selected leverages identical fuel tanks that can be connected axially or radially. This allows for the tanks to be arranged in a variety of different ways, almost like Legos, depending on the amount of fuel needed. As you can see, this platform currently supports up to 18 tanks, but could support more if needed. The components within the transfer vehicles are all identical. This lowers cost and complexity by ensuring that only one set of systems needs to be developed. The only difference between the vehicles is the number of tanks each requires. Additionally, this system increases the safety of the crew by locating the reactors as far from the crew as possible. Radiation to the crew is further reduced by the liquid hydrogen tanks. Throughout the mission, at least one tank will be full of liquid hydrogen, which serves as an additional buffer against radiation from the reactors. Finally, the transfer vehicles can discard radially mounted tanks. This further reduces the required system mass since each tank is about 5 tons empty. In order to maintain the center of mass along the axis of the vehicle, tanks are discarded symmetrically around the vehicle's axis. Depending on the geometric parameters of the vehicle, this means discarding either 2 or 3 tanks at a time. For a mission of this scale, some on-orbit assembly is inevitable. To assist with this, each transfer vehicle has a robotic arm similar to the Canadarm3 planned to be on the Lunar Gateway. In order to maximize the number of docking events the arm can assist with, outlets are available along the vehicles for the hand of the arm to plug into. This allows the arm to traverse the vehicle end over end and find a position to help dock any element of the vehicle. Having the arm assist with docking events minimizes the amount of RCS propellant that needs to be used for assembly. Fuel tanks are connected together via a propellant feed system derived from the system used on the Space Shuttle external tank. This allows the tanks to connect together at the beginning of the mission and detach when needed during the mission. Other elements utilize NASA docking system ports to dock with other vehicles. Using a common docking port among the vehicles allows for the various mission elements to move between vehicles without needing to worry about compatibility.
All fuel and propellant, including liquid hydrogen, liquid methane, liquid oxygen, and RCS, are stored in tanks made from aluminum lithium alloy 2198 due to its high strength and relatively low density. These tanks also include passive cooling, consisting of approximately 20 layers of integrated multi-layer insulation and 20 layers of load-bearing multi-layered insulation. This is applied on all transfer vehicles and the rover and will lead to reduced boil-off. LH2 tanks also utilize active cooling using a two-stage cryocooler to reduce system mass. The two-stage cryocooler uses a 20 Kelvin 20 watt and a 90 Kelvin 150 watt cryocooler for each LH2 tank. An aluminum broad area cooled shield is used to distribute cooled helium. This results in zero boil-off for LH2 storage. The MLI layers and other component arrangements are shown below.
Labeled diagrams of the two landers, Lander 1 and Lander 2, can be seen below on the slide. Both landers feature several common design elements, including 4-meter diameter fuel tanks and the outer exterior of these tanks being aluminum lithium 2198. Both of these landers also feature hypersonic inflatable aerodynamic decelerators, or HIADs, for the thermal protection system during descent. Attached to the HIADs are common descent engines, which are used for supersonic retropropulsion, and also descent tanks, which provide the fuel for descent. Lander 1 has a payload, which is the rover, and the rover deployment mechanism, which allows the rover to be deployed onto the surface. The payload for Lander 2 is the crew section and ascent system. The crew section houses the crew during descent and ascent, and the ascent system consists of the ascent fuel and the ascent engines. Lander 2 also features a ladder for crew egress. Lander 2 has a fully fueled mass of 53 tons, and Lander 1 has a fully fueled mass of about 25 tons. Lander 2 is about 15 meters tall, and Lander 1 is about 13 meters tall. So now onto the entry, descent, and landing systems, or EDL systems. A common EDL system is used for both of the landers to provide commonality between the vehicles. Both vehicles feature hypersonic inflatable aerodynamic decelerators, or HIADs, for thermal protection, and also use RCS to control this, to set the attitude prior to entry interface, and then use flaps to control the angle of attack and side slip angle during descent and prior to the engine ignition. Once the engines ignite, supersonic retropropulsion is used at 300 kilonewton LOX RP1 engines. These engines, in addition to slowing down the vehicle, also gimbal to provide control. These engines are built into the HIAD themselves and burn until the vehicles touch down onto the Martian surface. The HIAD remains attached and inflated until descent engine shutdown, after which it deflates. In addition, the HIAD also has swivel covers built into it that to expose or cover the engines and landing legs. This allows for the engines to be turned off and turned on multiple times if needed. Now onto the ascent systems of Lander 2. After completion of the surface mission, Lander 2 ascends back into orbit to come home. This ascent process utilizes the LOX RP1 fuel brought down in the ascent tanks of Lander 2 during descent. The ascent process utilizes 9 24 kilonewton engines. These engines are used after the vehicle does a surface staging maneuver and leaves the descent portion of the lander on the surface. After ascending, the ascent system achieves a 300-kilometer orbit and a rendezvous with Transfer Vehicle 3. Once rendezvous has occurred, Transfer Vehicle 3 transfers the crew back onto an aerosynchronous orbit where they can rendezvous with the remaining crew members who have been in orbit.
Rover 1 operates as a mobile habitat for the surface mission. The base chassis is made of 3 cm thick aluminum 6061 with rough dimensions of 3 by 3 by 6 meters. Rover 1 has a total mass of 14.44 tons and an internal volume of 44.75 meters cubed. The interior is split into the living quarters and the suit chamber. Therefore, the habitable volume is actually 33.51 meters cubed. The living quarters includes the cruise chambers and the cockpit. The suit chamber acts as an airlock for the rover and a storage chamber for the crew's 2 XEMU suits. Rover 1 is capable of both autonomous and manual driving. Rover 1 drives on 6 spring tires developed by NASA engineers. The wheels are made of a shape memory alloy, nickel titanium, which is resistant to damage caused by the harsh Martian terrain. SOFCs are utilized on Rover 1 to generate power. They use liquid methane and oxygen as propellants. Both liquid propellants are stored in tanks on the exterior of the rover. Next to the methane tank is the rotary percussive drill used to collect the samples.
The Rover 1 life support system is very similar to that of the crew module, with a few key exceptions. The first is that while the crew module uses many regenerative systems, the rover uses more simple storage systems for water and oxygen to reduce the mass and complexity of the ECLSS, as well as improving reliability. Additionally, while on the surface, a prepackaged and thermostabilized food system is used for the same reasons. Because Rover 1 has a much shorter mission duration than the SHIELD crew module, but uses many of the same technologies, the ECLSS reliability, as calculated for the crew module life support system, increases to 99.8% for the rover, which is a 1 in 511 chance of running out of spares.
The drilling will be completed by a rotary percussive drill built by Honeybee Robotics that is currently being tested by the Atacama Rotary Astrobiology Drilling Studies team. The drill has the capability of reaching 1 meter in depth with the purpose to create core samples that will be sent back to Earth in search of life signatures on Mars. Each sample will be individually packed in a test tube to prevent cross-contamination. These test tubes will then be packaged together in a storage bin. In addition to the test tubes, witness tubes will be utilized at each drilling site. These tubes will be empty tubes that are exposed to the atmosphere during drilling and rule out the possibility for false positives of the core samples. After each site, the drill bit will be replaced. This is done by disconnecting the drill bit while it's in the ground at the last location of that site, then dispensing a new bit from the spring-loaded magazine mounted next to the drill on the side of the rover. When determining the precise location of drilling, the mounted supercam will be used to select the most desirable locations based on rock composition, among other factors. While the drilling is happening, the astronauts will be completing EVAs in which they will collect surface samples for analysis aboard the rover by other science experiments. The first of these instruments is the Signs of Life Detector, or SOLID. This instrument uses multiple biochemical methods of searching for life signatures and can detect 512 unique compounds. The other instrument aboard is the Potassium Argon Laser Experiment, or CARL for short. This instrument can date rock samples, and the data can be compared against other Martian drilling sites.
The first day of the mission is spent inside Lander 2 to let the crew acclimate to the Martian gravity. Rover 1 is not at the landing site of Lander 2 upon arrival of the crew. Rover 1 drives autonomously to the landing site during the first day to rendezvous with the crew. Over the rest of the trip, 19 days are allocated for driving and 8 days are allocated for drilling. The final day is for transferring back into Lander 2 to leave the Martian surface. 1 extra day is left unplanned as a safety factor. On the days of driving, Rover 1 will drive for 16 hours per day, requiring an average speed of 9.68 kilometers per hour. The trip follows a triangular shape spanning parts of both Amazonas Planitia and Arcadia Planitia, making stops at both the Erebus Montes mountain range and the Milankovitch crater. On the days of drilling, 3 samples are taken at each drilling site at a minimum of 15 meters apart to prevent cross-contamination.
During the development of SHIELD, there will be some risks that need to be monitored. The major risks are shown in this risk matrix. While risk mitigation strategies have been accounted for in the design, there are still influences outside the immediate control of the program that could delay the program and/or cause cost overruns. For example, while adequate money and development time have been given to developing an LEU CERMET reactor and a ZBO system, it is still a possibility that technological limitations prevent these technologies from maturing on schedule. In the case of the LEU CERMET reactor, this risk is further mitigated by the potential to switch to an LEU composite reactor if development of LEU CERMET is slower than anticipated. Another unknown that could interfere with the program is government funding. SHIELD will need to maintain funding through multiple administrations. This risk has been mitigated by using unproven technologies only when necessary and spreading out the mission costs as much as possible, but it is still something that could cause problems in the future. Risks associated with launch vehicles are mitigated by sizing all elements of the system to fit within a New Glenn fairing. By doing this, both New Glenn and Starship would be capable of carrying all mission elements to low Earth orbit for assembly. Having multiple potential launch vehicles mitigates the risk that none will be available and that the launch schedule will be too aggressive for one company to undertake. Throughout the process of designing SHIELD, we strove to make it safe for the astronauts, maximize the valuable scientific data acquired in the search for life, and keep the cost of the mission down to a reasonable level. Every aspect of the design, from the eclipse to the selected orbits to the mission timeline, were designed with these three ideas in the front of our minds. As a result, we created an architecture that best satisfies the objectives and requirements outlined by the theme statement. Thank you for listening to our presentation, and we will now take your questions.